this sequence is our main focus. Usually around 300 BC show that like this set is infinite. So all this set P set of primes, and N stands for the set of natural numbers for us, which like 1, 2, 3, etc. This is our set N. So we did show that the set or P is infinite, and the argument was as follows: since if P1 to Pq were the finite sets of primes, then this number has some dimension which doesn't belong to the set P1. So the set of primes that is right. So here is your first homework. Show that. Pk plus 1, that is, if you denote that P1 is 2, P2 is 3, and so on, Pk denotes the kth prime. This is the k plus 1 prime. Show that this is bounded by 2 over now, wouldn't it be very nice if we had a formula where we could put the natural numbers? So something like, would it be nice to have a formula like we want to, I don't know, give some function of natural numbers, so that this is always giving the primes. You get all the primes just by inputting the natural numbers into this. So the question: does there exist a multivariate polynomial with integer coefficients? Such that for integer inputs, not integer, sorry, natural number inputs, for integer inputs is the package. Or this is a multivariate polynomial that is yeah, okay. So suppose you put plug in natural numbers there. We will give you always the set of always primes, and in particular whether you can get all the primes for that. So suppose even if we don't ask that whether we get the entire set of primes, the question is whether this can always have prime outputs. Okay? So does there exist a multivariate polynomial with integer coefficients such that for all x1 over xn in the set of natural numbers, f of x1 over xn is prime. So what's your case? Can there be such a multivariate polynomial?
First, we can ask for univariate.
Sure. How would univariate? So just make a guess. You don't have to give the complete argument immediately. What do you think? Such a thing should exist? Yeah.
No.
And so then your task becomes is to show that it doesn't exist. So when it doesn't exist, multivating polynomial to this property. And it will always give prime outputs for integer, positive integer or integer inputs. However, this is true up to very small modifications. Okay, this goes to 1, and then there could be a second part of this question. The second part is what happens if we allow rational coefficients instead of integers. Okay. So the coefficients of this, you are allowing them to be rationals, and still the main question remains the same: whether there exists such a multiplied polynomial which will always take prime numbers. So this. Yeah, the answer to this one that whether such polynomial exists or not is negative. However, there is a result by Jones, Sandoval, and James from 1976. So here is equivalent. Jones, Sandoval, and James from 1976. It says that there exists multivariate polynomial with integer coefficients such that for all x1 with multivariate polynomial, all this again if, or we can just write there for all integer inputs. Positive integer inputs. The positive values, so here we are allowing all the values. And here we are saying that the positive values attained by the polynomial, or the positive values output by the polynomial, positive outputs of the polynomial, sorry. All the times. The data set is covered by the outputs of such a thing. And they indeed actually provide an example of polynomial of 26 variables. So there are exactly 26 letters in the English alphabet, so it covers all of them, and 26 variables, and the degree of that is 25. Can I invite these two ones out? Thank you. And that is not the only polynomial of course. So let's make a small table of the constructions, variables, and here is the degree. Even before they produced this explicit polynomial, there was a construction by IISER with 24 variables and degree 37, which had the same property. Then their construction was, well, IISER in 1970, actually his theorem was that every enumerable, computationally enumerable set is diagonally. That is, if you have an algorithm which outputs all the things in your set, then you could write such a polynomial whose positive outputs would give you the set of all the elements in that set. So it is not, it's nothing specific about the set of primes. Every set with computationally enumerable, for that such a polynomial will exist.
Computationally enumerable
means that you know how to compute how to compute that. Okay? So such a set would be called computationally enumerable, and there will be a definite description of that. That is IISER from 1970. And this was his first construction. He outlined a construction of such a polynomial with 24 variables, which is degree 37. Then there was another thing, another such construction which also is sketched. It was 21 variables, 21 degree, and then they give such an explicit polynomial in 26 variables with degree 25, and the list continue for some more variables and degrees. So they also, there are different constructions that they make. So for 19, the degree was 29. For 42, it was 5, and 5 was the smallest degree which has been obtained so far. It's difficult to control both the number of variables and the degree. So it's an open question here whether there exists a such polynomial of degree less than 5. So it's an open question. Degree less than 5, is it ever possible? And they also showed that 12 finding is possible, but they said that the degree would be very large. They didn't compute the degree explicitly. They just give the construction and said that it will be a very large degree. So you don't, at least the paper doesn't mention that explicitly. Now, another open question is that how far the number of variables can go down. So is it possible to get 2 variables, for example? And this also leads to a small homework. So this is third one actually. All these homeworks which we are giving today are accessible with elementary means. So you don't need any specialization or any analytic techniques, of course. This is the third one. Well, at first let's begin with this question. Suppose you have such a polynomial with a single variable, such that all the positive outputs of that are giving you prime values. Is that possible? So, or all the positive outputs of that are covering the entire set. If not, the entire set, at least it's taking arbitrary large prime values. So, does there exist a single variable polynomial ZX such that if you input the natural number, so if number outputs. These. This is P, the set of all primes. So this is suppose this is the third one. So this is also elementary, and you will guess the answer to that already from here. You're asking whether the degree can go to a certain number of variables can go down to 2, but not asking whether it can go down to 1, because 1 is not possible. So the answer to this is no. But then your class becomes to show that such a thing doesn't exist. Alright, now it's almost 9.
Is that an open question? Like 12 to 1?
12 to 2.
12 to 2.
12 to 2 is an open question. I mean, whether it could be brought down to 2. And whether the degree, it may not be the same thing, which is having number 2 in here and degree 5 here. But nevertheless, this is a separate open question, whether the degree could be brought down to something which is less than 5. So instead of looking at formulas for which are producing primes, we will turn our attention to some other things, which are sums over primes, different sums over primes, and this we'll do in the we'll begin with this in the next class, but let's write it down which are sums we consider. So the first one is called IIS, the set of all primes less than equal to yes. P here goes up and yes. Right. Then the sum of reciprocals of the primes is less than equal to x. Well, and this also provides some products, right? So here we have the product of P less than equal to x. Product over 1 minus 1 by P less than equal to x. And here sum over log P by P less than equal to x. Why we are considering all this? Well, you can understand that this is of course a divergence case. Summation 1, since there are infinite primes, this diverges, right? So this is pi x is an estimate, pi x is a number of the primes which are less than equal to x. And this one will show that this series also diverges. And so this is an estimate of, if we put estimate with sum in terms of x, then it will give you the order of growth of the series, how it goes. Then there is this one. Similarly, we have a distribution of this, a number distribution of this in terms of x. And here also there is something called Martin's theorem that we get from this. Okay. So that was 5th, and here is that was the 6th one. Summation over P less than equal to x, and P is in some identity progression. Okay. So, for example, Euclid's proof. This is the last thing that we are going to see. We can go to the next lesson in a moment. So, the Euclid's proof actually shows that the primes on the natural numbers are infinite. Is there any subset of the set of the natural numbers where the set of primes are infinite? Can you see it from Euclid's proof? Any proper subset of the set of natural numbers where the set of primes are infinite, whether infinite set of
Trivial.
Yeah.
Some trivial subset.
Yes, kind of
Odd number.
wonderful. Yes, if you take the odd numbers. Also, there are easy ways to show that there exists infinitely many primes the things, 4n plus minus 1. 4n means just you are taking the multiples of n, natural numbers are 4, and you are adding or subtracting 1. And also in 6n plus minus 1. And so on. But nonetheless, instead of 4n plus 1, 6n plus 1, if we take an arbitrary arithmetic progression, we will there exists an infinite primes in that remained an open question for quite a long time. So Euclid proved his theorem about 2700 years ago, and only in 1837, which is less than 200 years from now, there was a theorem by Dirichlet which said that if you take any arithmetic progression with the first term and the common term co-prime to each other, that will contain infinite primes. That is really so. So, and this was basically his idea, that is understanding some of the reciprocals of the primes. Well, this is actually based on this idea, which was by Euler. Some of the reciprocals of the prime, if they diverge, then there are infinite primes. So this originated with Euler, and he predicted actually was intuited like this, and he took such primes in some arithmetic progression. So p less than equal to x and here, and p belongs to say a plus dx. Consider all these primes which are of this form. Then the sum diverges. So that was his idea. We'll see all these estimates in this course. And that's all for today's class. You will go and develop common sense. See you again on Wednesday.